Okay, as you can see, the title is Limit Periods on Curves and Arithmetic Heights. So I will present in that order. So I will begin with what I mean by limit periods, and then I will end by talking about arithmetic heights. And this is joint work with Spencer Bloch and Robin de Jong. Now, we're going to start by taking a degeneration of curves. Start the time as well. Now, here's technically what we mean by that. So the degeneration of curves is going to be first over a complex disk, so one-dimensional complex disk, and the total family, let's say pi, with projective, flat, all the nice adjectives that you want to put. The total family you want smooth, but alternatively, that's just reasonless squiggly lines. The family is X. The disk is here. And I want my general fiber to be smooth. So let's say it's fiber over T. It's XT. So it's smooth everywhere, except I want simple nodal central fiber. That's over 0. And let me just write these things. XT, fiber over T is going to be smooth. Genus G. And then X0 has a simple node. So it's little x. Basically, it's the simplest possible degeneration you could possibly imagine. That's what we're doing. And now what we're going to take with this are, well, we can take the periods of the nearby fibers around the origin. So we have these pure Hodge structures. And these pure Hodge structures have a limit. There's something called a limit mixed Hodge structure. Now, for technical reasons, I will twist this Hodge structure. So if you know what it means, you know it doesn't mean anything. If you don't, I mean, you can just say it's there's an integral lattice inside. You're basically multiplying this integral lattice by 2 pi I. It's not very important. But so these pure Hodge structures have a limit. The thing is, the real limit you're taking is like the space of holomorphic forms inside H1. And so this is a point in the Grassmannian. So it's a G-dimensional space within a 2G dimensional cohomology. So let's write this down maybe. Without the twist, this is the point in the Grassmannian. So you can think of the integral structure tensor with C. The space of holomorphic forms is a point in this Grassmannian. So I have a locally trivial fibration, so that this space is locally constant. So I can pretend I understand how this thing moves within a fixed Grassmannian. The problem is that the way this moves is terrible. It has its coordinates, and let's say particular coordinates would have logarithmic entries. So you cannot take a limit, although the space is projective. So it blows up and it diverges in a crazy way. But anyway, there is a limit. But the regularization and defining a limit requires you to correct these logarithmic poles. And that means you need to understand what is log t. And so this limit becomes sensitive to what is your limiting parameter. Or more precisely, the infinitesimal rate at which you approach is 0. And this I will call psi, which is, let's say, the differential of t at 0. So this would be a differential at 0 at the stop. All right. And now that I just give a name to this limit. And again, I put this limit in quotation marks. This is the limit Hodge structure. And of course, this is, because it's a weird limit, it also, it acquires, in fact, a mixed Hodge structure. Fine. And I can explain, and we need to talk about the very structure of arXiv. And the crudest thing you can do is to break arXiv into its weight graded pieces. Now it's a mixed Hodge structure. So besides the Hodge filtration, it has this mixed weighted filtration. And so I'm now going to write the graded pieces. So the first piece is one-dimensional. It's essentially Z. Again, there's this twist. And then I have H1 of the normalization of the central fiber. I will write it down in a second. And then another copy of C. So where C is the normalization, desingularization of the central fiber. So maybe I draw my pictures over here. So I want to explain also the elements corresponding to these items. And to be able to draw pictures, I'm going to make one simplification. This you can identify by the homology of the curve, and this too, this twist you can identify with. Hence, also one of the reasons for the twist. That means I can sort of represent my elements by loops on curves, so I can draw pictures as well.
So you're assuming the center fiber is reduced.
Sorry?
You're assuming the center fiber.
Oh yes, sorry.
Simple.
And my picture tried to say this. So let's draw our picture. So initially, my XTs looked like this, and they degenerate to a normal curve. And then I'm normalizing the curve. So I have my P and Q, which will play a prominent role. And you can see a bunch of things that, for example, if I take these loops here, they kind of survive the whole limit process, even survive up to the normalization. And you can sort of squint and see the homology of C appearing without being messy. One of the key players is the vanishing cycle here. This kind of element, as you can see, becomes something that contracts. And here it becomes just a loop around the point, which it will again contract in C. And I think I called this beta. So it turns out that this element, this is generated by beta. And then the other element, significance, is what's called the co-vanishing cycle. So these are not uniquely defined, but alpha is not uniquely defined. You can add another loop. It has the property of intersecting the vanishing cycle. And again, it becomes something strange in C because the homology of C would not allow a cycle with endpoints. So it becomes an element of the relative homology. But so this alpha becomes one of the additional elements. Okay, so now the periods of arXiv, so sort of its Hodge structure, carries a lot of information that most of it is known, and one part of it was not known. So first of all, or I should say, mixed Hodge structures that are of this type, where you have two Z extensions on two sides, something pure in the middle, are called bi-extensions. Because the mixed Hodge structure is first an extension of this, of the middle piece by Z, and then of that by another extension by Z. And so here's what it gives us. So we know the following. Even the central piece recovers C. This is Torelli's theorem. So the limit mixed Hodge structure knows already a lot about the central fiber. Second, the additional extensions, the two extensions, know about P minus Q. So this could be viewed as a element of the Chow group in C. And here's how we can represent this. The extensions so this is the weight minus one part of L psi gives me that extension. And the other one is I mod out by that element, it gives me the remaining extension. So these two are extensions of simple extensions of H1, and both of them give me the about Abel-Jacobi image of P minus Q. So the Jacobian of the curve can also be viewed as can be identified with the extensions. And so you sort of lift the section projected back down here, modulo your choices in lifts, you get a well-defined element of the Jacobians. And that ends up being the about Jacobi of P minus Q, which means, for example, what do you know? I mean, so for instance, if C is not hyperelliptic, this will tell you P minus Q. You will be able to recover the central fiber completely. But we did not yet use the full knowledge of the bi-extension. One graded piece already gave me C. Then I used the extensions, and they gave me P minus Q. But the bi-extension carries more information than these two extensions. It sort of puts the two extensions together in a non-trivial way. So the family of bi-extensions specializing to two fixed extensions that can be identified with C star. I'll talk about this total family later on, but given these two extensions, there is another family of bi-extensions. And then the question is, what does this extra information give us? All right, so let's talk about, let me make this C star a little bit more precise by talking about the limit of holomorphic forms in L psi. So remember, there's a shift. So the holomorphic forms which were F1 become F0 after the shift. So this is this G-dimensional subspace. This is 2G dimensional, this is G-dimensional. So what you can do is to represent it as the span. I mean, you can choose coordinates, let's say, and try to represent this as the span of the rows of a G by 2G matrix. And what I'm going to do is I'm essentially choosing holomorphic forms. And I've chosen my alpha and beta here. And in between, I'm going to choose the basis for. So these parts should be the gamma i's and the basis homology for C. And the first pairing, so the middle part is just, I'm integrating holomorphic forms. They have a nice limit. They become holomorphic forms on C, integrated against loops. This is just the period matrix of C. Holomorphic forms against vanishing cycle just give us 0. I can choose my remaining form so that it has a period 1 against the this cycle. So it means I have a metamorphic form on C that has residue 1. These parts are the Abel-Jacobians. They're lists, so they're representatives of the Abel-Jacobi class. It's an element on the torus. These are vectors. So 2 different ways of representing the Abel-Jacobi. So these are the items that we know about. And then what is this? Now this is strange because if you try to interpret it in the way that I've just done, you must integrate something along this path. And what is that something? Is that it's something that has poles at P and Q. It's a metamorphic form with poles P and Q. This integral blows up. And hence, we're back to where we started about trying to define the limit. There are logarithmic poles. We normalize these logarithmic poles. And we got something in return. And so same thing intrinsically happens in C, that you cannot a priori make sense of this number. It would be infinity. And well, so, but there is a number, there is some number. So we don't know what it is intrinsically, except there is this number. But okay, we have some hints. So we were asking, what is this? Right? This is the precise version. And okay, it's a complex number, but modular choice of basis, it really is something in C star. So the C mod Z. And well, the answer to what is the significance of this number, the first hint we get is from the following book. So it's a great book. I love reading it and I recommend it. It's called Period Mappings and Period.
So it's a new edition.
There's been a
New edition
how new?
this year.
This year, oh, maybe I should check. So, but in the previous edition, so there's a quotation. So they write a period matrix just like this one. They give it a different name, but so I paraphrase only the symbol. Let me write exactly. So they say the value, so star in our language, has no significance. Right, and well, the point of this talk is the significance of psi, of this number's star. And well, of course, they're not wrong. Right now, one thing they realize is that if you scale our deformation parameter t by some complex number lambda, this thing changes by log of lambda. Then star changes by log of lambda. I mean, lambda is a complex number, but this 2 pi I is sort of unimportant up to changing coordinates, so I don't care about which branch of logarithm you take. So log of lambda, basically, it means by scaling my parameter, I can hit any number I want here. Therefore, it cannot have any significance. That's what they say.
Can I ask a question?
Yes.
So you mentioned the variation of mixed thought structure, but isn't this exactly what happens, for example, at maximal unipotent monogamy points? So there, the star would, so you naturally just get rid of the leading diverging singularities, and there's a well-defined meaning for the remaining of the period. So you can you have periods which have some leading singular behavior, but there's still, for example, power series in some underlying modulus that has a well-defined meaning, and that would be sort of the natural thing to
it seems to me that these, okay, first of all, some FPs make sense, and people know that they make sense. But traditionally, what happens is if you have a limit mixed Hodge structure, something like half of it is about the mixed Hodge structure of the central fiber. But then there are symmetries, and you say basically the bottom part is symmetric to the top part. You remove the top part and then study the bottom part. What I'm saying is that there are some extension periods between the top and the bottom that carry extra information. And in general, it cannot carry any geometric information for this reason. It's a priori meaningless within this context unless you introduce more information.
Well, algebraically, it will, because.
Yes. I mean, you need to put one more, we need one more.
Yeah, analytic continuation.
Yeah. I mean, of course, in real life, you never take, I mean, yes, we always talk about a complex this, but in real life, your complex this might be a neighborhood in a quasi-projective variety curve, and then there's this curve is defined over rational numbers or something, so you have restrictions on t that you would take, right? And this is where I'm going. But even better, you can even simplify it. So I'm going to assume as little as possible, and here's the minimal version. So you could have taken the base to be a curve, but even less. So on the other hand, this says there's no meaning, but if our curve, so the central fiber was x0, normalization is C, let's say C is defined over Q, and so are the 2 points, so they're rational points of C. Of course, any number field would work, but that's not what it is. So if everything is defined over the rationals, then we can use the sort of, let's say, baby Hodge-Spencer map. So I'll denote this by kappa. So the tangents or cotangents, it doesn't matter. Everything is one-dimensional here. I have a map from Hodge-Spencer to the following. Yeah, so Hodge-Spencer in general for singular varieties gives you a map to extensions of the cotangent bundle by the structure sheaf. A significant portion of those extensions are called these locally trivial extensions. They do not smooth out the singularity. And there's a quotient space, which tells you exactly how you are smoothing out the singularity, how you're changing the local geometry of the singularity. So this is a very small portion of the Hodge-Spencer map. But if C is defined over Q, my points are defined over Q. These cotangent spaces naturally are both have a Q structure. So I can say this is a natural Q inside. Yeah, so maybe these are the omega C, let me write this, omega C over Q, answer omega C over Q. Yeah, so this is isomorphic to Q. Now already that means I can just transport this rational structure over here, and I can say, well, if my psi is a rational number, and I would like it to stay a rational number, then my indeterminacy changed from scaling by a complex number to changing by a rational number. So if we insist this Hodge-Spencer image of psi is rational, then the number becomes well-defined modulo logarithms of rational numbers, which is significantly better than nothing. I mean, real numbers are uncountable. This is countable. So suddenly, at least theoretically, this carries a huge amount of information. Of course, logarithms of rational numbers are dense, so it maybe doesn't look nice, but already this is something. And well, we will see towards the end of the lecture that you can do better. You can put an integral structure here by choosing a regular model of C over the integers. And then it becomes so the right-hand side is this. This is the right-hand side. There will be a Z inside, which means I can insist kappa xi to be a generator now of this ring of these integers. So if we insist kappa xi is a generator, then this is well defined. And now something must happen, really. We essentially have a well-defined number. It must have a significance, but it's also clear that this significance must come from arithmetic information because I use C over Q and even the integers. And so this is the vague formulation of our theorem. So I have introduced about half the notation. Is that so this thing basically computes an arithmetic invariant of P minus Q, what's called the Neron-Tate height, P minus Q. So the rest of this talk is about fixing the statement as I presented it. First of all, we need to correct what I mean. Basically, there is some messiness here. I did choose coordinates, so I need to be careful to make this now independent of my coordinates. But there is something independent of coordinates, and it almost computes the height. So we're going to make all of this precise. And towards the end, I will describe this what this height means. It's an arithmetic self-intersection number, and give the exact formula relating the two numbers.
Which means Carlson revised a book too early. Has waited one, should have waited one more.
Too late, yes.
And can I maybe just
Yes, please.
So this includes the elliptic family of elliptic curves, right? So then the period matrix that you wrote down will only have the entry star and 1.
So this,
but there you're saying it's not clear what star should be, because I think from the variation of, so the limiting variation of Hodge structure and this degeneration would tell you what star it should be. So you have 2 periods for the family and normalize 1 to 1. The other one will be log T, and then plus some power series.
So what I'm saying is that if you have an elliptic curve degenerating to something, it's degenerated to P1 with a node. And on P1, the Neron-Tate height becomes exceptionally simple. It becomes something like a cross ratio like formula. That's why people sort of by hand calculated what this limit was in that case. But I don't think they related to the Neron-Tate height, and for sure they don't relate it to the Neron-Tate height in general. But this is the one case that.
So I was just wondering this procedure of getting rid of the logarithmic varieties.
Yes.
So this is also generalizable, and this should give you.
Oh, yeah, I mean, that's the definition of limit mixed structures. That's the definition of limit mixed structures.
Yes, but then star is not. There's no question mark.
No, there is
Okay,
because you're doing a transcendental change of variables, and if everything is defined over a number field, that's not going to be allowed. So you know your transcendental change of variables will modify star. So if you want to have a formula, so that's what we say.
Okay.
I had a vague question. So there is a similar, like an old story about trying to understand the secondary extensions in the weight filtration for limited P-square structures, which is so it's this theory of Annette Huber for describing the secondary extensions in terms of polylogarithms. And so there was some subtle story there that over the reals everything splits in the secondary setting, but if you try to do it over the rationals, then it's completely unclear. And she actually computed some values which look like zeta values or multiple zeta values that would be an obstruction, but there was no clear geometric or arithmetic meaning for those. Is there any relationship?
Yes. So I'll actually write down the real splitting.
Okay.
So it's true that these bi-extensions, or I should say, the section is now called height of bi-extensions. So I want to. So the reason I'm talking about this right now is to make this star entry, which I erased, well defined, but it relates to exactly what you're saying. There's the bi-extensions usually do not split. And oh, it's unfortunate I erased what I had, but so to make with a definition of star independent of coordinates, one of these ideas is to study how it would have split if you forget the integral structure. So this is the sophisticated version. There are two versions, but since only asked this question, I will start with the sophisticated version. So there's a moduli space by extensions. Let's say of H1, C1. I mean, any pure Hodge structure of weight -1, that's what you take. This becomes identified with the Poincare bundle or the Jacobians. So this is Poincare bundle, and you subtract the 0 section. And let me just remind you that there's a projection to J's with Jacobians, and this is a C star bundle. And there, I mentioned a C star, that's the fibers are these C stars. So what we're hitting, these are the extensions. So I start with a bi-extension, I split it into two extensions. Those two extensions hit here, and then the fiber is C star. Now that's a lot of information. One thing you can do is forget. So this cancel with real numbers and look at moduli of real bi-extensions. Now here, all extensions are split, so you lose these moduli, and these C stars become, so this C star was actually C mod Z1, Z you tensor with R, this becomes R1, and then the quotient becomes the real numbers. And this becomes canonically identified now with C mod R1, which is canonically the real numbers. And this measures the obstruction of the real splitting. And there's a definition of pain from 1990s that says we define the height of a bi-extension. Again, now I'm talking about our arXiv, but any bi-extension is defined as the maybe this map I should represent by obstruction. So the identification of the moduli space of the real numbers is that you forget the real structure and then compute the obstruction. Remember, this is a real number. And so one of the observations that you can make is that the star is essentially measuring the height. And so the unsophisticated version is that, remember, we had a period matrix which I erased, but let me briefly remind you. There was a omega g giving me the last columns. Well, if omega g, which you can view as an element of metamorphic form on C with poles at P and Q, and the residue is, well, pole residue 1 at P and -1 at Q. If this thing has purely imaginary periods on C, then star is the real part of star is well defined and it is the height. So what we're saying is that the bi-extension height is basically measuring Neron-Tate height. Now, you also asked about the rational structure. So if you forget the integral structure but replace it with the rational structure, it's going to become more complicated because of these Jacobians. Anyway, this is something in between. Right, any questions? So what we did right now was to improve our statement star to something that's at least coordinate independent. It's going to be replaced by height. And one of the reasons that, well, Spencer originally conjectured that there should be a relation between these two numbers. And one of the reasons is, as Tony pointed out, that bi-extensions are frequently used to compute Neron-Tate pairings, Neron-Tate heights. And but you use a different kind of bi-extension, and this bi-extension does not fit into that framework, the kind of bi-extensions that are used. So there's a class of bi-extensions which is very natural. We know bi-extensions are used to compute heights, and yet, so this was sort of hidden in plain sight. This was not interpreted. And the reason it was not interpreted is it's very difficult to get a arithmetic handle on this because it's a limit mixed-Hodge structure, and you don't have the construction of limit mixed-Hodge structures in, say, the theory of motives or something. The functors don't work there. Well, anyway, so just to complete the answer of the statement of the theorem, I need to talk about now arithmetic intersection theory. So the goal is to complete the statement and give you a precise identity between these two numbers. And well, okay, I said we start with a curve over the rational numbers. So you pick a regular model. I'll denote it by script C over Z. So this is a regular scheme over the integers. And here's the picture you can have in mind. So the integers are one-dimensional, C becomes two-dimensional. So the generic fiber is our original C, and we had 2 points P and Q here. But in general, you can sort of reduce the equations of C modulo 2 and get another curve over F2, the field of 2 elements, or reduce the equations again and maybe get a singular curve now over 3, and so on. So in general, the reductions will be smooth, but there will be finite many primes over which the reduction becomes single. Now it's certainly a fascinating chapter in history where they were trying to develop intersection theory on arithmetic surfaces. This is two-dimensional, it's called an arithmetic surface. It doesn't behave like a proper variety. So because sort of spec Z is not complete in some sense that you can sort of escape from here. So they could not define and it's clear that you cannot define intersection theory that's invariant under rational equivalence. Just like in real geometry, I mean, actual geometry, where you're allowed to move cycles by rational equivalences. And the degree map doesn't make sense. Even if you were working with spec Z, rational functions are rational numbers, the number of prime divisors of a rational number can change. So it doesn't add up to zero. The poles and zeros don't add up to zero. So what they realized quite early on was that you should look at the spec Z points of this variety. So the generic fiber you switch, and you essentially place by a Riemann surface. What you do is, one way of interpreting it is that you use the Riemann surface as a bookkeeping device, so that when you do a rational equivalence here, you're going to change some quantity on the Riemann surface. And when you sum up the two quantities coming from geometry here and analysis here, you acquire independence under rational equivalence. All right, so the quantities we need to introduce is, given a zero cycle here, so a bunch of points on the living here, sort of away from the generic fiber, we will define the arithmetic degree, but the finite part of the arithmetic degree. So you would like to count the points, but the thing is, if I have a point here, I'm not going to count it as 1, I'm going to count it as log 2. And if I had a point over here, I would not count it as 1, but I would count it with weight log 5. So let's say point over P is counted with weight . I mean, you can later exponentiate if you didn't like log P, but the whole point is that this additive structure allows us to sort of capture, using the complex numbers, what rational equivalence does on the geometric part. So this is, and on the analytic part, the bookkeeping device is quite strange. You take, let's give it a name. So I'm going to be interested in something like intersecting, sections like this. They can of course intersect in the rest of the surface. I'm going to be interested in intersecting such sections. So given a section like P minus Q, I'm going to take this holomorphic form with poles at residue 1 at P, minus 1 at Q, with purely imaginary periods. This is standard. And now there's one more thing I would like to do. We're going to talk about the intersection product of points on P and Q. What I've done here were the closures, the risky closures of these points. But there's now a model dependence. And so there's one way to factor that into account. You can change the model and then the numbers will change. So there's one more bookkeeping device, which is actually fascinating. I've given an entire talk on this quantity, but I will not do this now. So this is a vertical, meaning it lives only on fibers, vertical Q divider, such that phi plus P minus Q, rather the closures, is of degree 0 on every component of every fiber. So the issue here is that P minus Q specializes here to P here and minus Q here. So that along this component, I have degree 1. Along here, I have degree minus 1. But the total degree of P minus Q and then is not 0 on these components. So this is a way to correct it. By adding a bunch of these vertical divisors, you make it degree 0 everywhere. So this is it's simple and annoying that you have to keep track of it. But it turns out it's so important that it's one of the main obstacles in doing intersection theory in higher dimensions. You don't know if such a phi exists in higher dimensions. And I will say this briefly in passing, that the contribution of phi in our formula looks like a tropical phi extension height. But there is no tropical mixed mode structure theory, certainly no tropical heights of phi extensions since they don't exist. But you can write down what it evaluates to, and the formulas look structurally similar. So it has quite a lot of significance. Okay, so here's how the first step of the intersection theory is that if I have P, Q, R, S in C, distinct points, then you define the Neron-Tate pairing like this. So you take an integral from S to R of this form that I just described. This is going to be path independent if I take its real parts, because all periods of omega are imaginary. And then you add P minus Q, phi. You intersect P minus Q with this correction with R minus S. And it's a zero cycle, it's just usual intersection theory. And then you do the arithmetic count. It turns out that this is invariant under rational equivalence of dividers, meaning of R minus S and P minus Q. And independent of the model. Yeah. And now I'm going to use rational equivalence to tell you what it's like. We define it as you want to intersect then something in the rational equivalence class of P minus Q with something in the rational equivalence class of P minus Q, but they should have disjoint supports. Otherwise, this intersection product doesn't make sense. So it's where this is in here, this is in here, and these don't intersect. And so this extends, of course, linearly to more complicated degree 0 divisors. This can be sum of PIs and QIs. And okay, a brief rant about this intersection theory. This is not how you do intersection theory, how you do self-intersections in proper geometry. You have like Porteous formulas, self-intersection, excess intersection formulas. We know how to compute self-intersections without moving them away from each other. It's only in arithmetic theory that they do not have such a formula. It's very interesting that it doesn't exist in curves and it doesn't exist in higher dimensions. And this difficulty of having to move cycles from one another actually is even worse than in geometry, because you have very few points. So in theorem, a curve of genus at least 2 will have only finitely many rational points, right? So you cannot actually move points away from each other easily. It's a huge hassle in computation. And in arithmetic, every object you find is like a special gem. You would like to compute its self-intersection or something. And now this sort of breaks the symmetry. And you have to pay for breaking the symmetry Okay, so what we are doing morally with these limit mixed for structure is we're taking like a deformation to the normal cone kind of argument. This somehow deformation of the nodal curve to smooth curves locally mimics a deformation of the normal cone of P and Q. But okay, so this is just a rant. Let's continue with the talk. Okay, so I think I have almost everything to write down the correct statement of the theorem now. So I want to say the height, the Neron-Tate height of P minus Q is the height of psi. Now you have to pay for choosing a stupid psi if you've made a bad choice. So I'm going to write it like this. I'm going to explain what this is. Plus the intersection of P and Q and the arithmetic count. So for example, if they intersected over 17, it's log 17, but they could intersect over many points. And plus the intersection of P minus Q with their correction divisor and the finite count. Okay, so that's the theorem. All of these numbers are moderately easy to compute. So the numbers over here are easy to compute. It's a transcendental number that's usually very difficult to compute. One of our motivations for trying to build this formula was in higher dimensions. I will say a few things about higher dimensions. The left-hand side, both valence and heights, are essentially impossible to compute in practice. Whereas, for instance, I have a code that can compute limits of Hodge structures and their heights, which means this opens a door to computing both valence and heights in higher dimensions. Oh yes, the psi. Let me give you a psi. Remember, we had the Spencer map. And in here, I could construct the cotangents of C along P and Q. So P is like a Z section. You pull back the tangent bundle of C to your Z. So this is isomorphic to Z. And now I can take like a generated one here. It's unique up to psi. And I define the norm of psi to be lambda, sorry, absolute value of lambda, if the codarius tensor of psi is lambda times 1. And the absolute value fills the indeterminate. So this is now well defined. In particular, if you've chosen an integral direction of deformation, this is 0. I should point out that if you choose a good model for C, you can blow up the points of intersection. This can also become 0. Both of these are local contributions from the node. They don't care at all about the full geometry. So you really have two interesting numbers, this height and that height. And that's what I was saying, that this looks like a non-Archimedean, even a tropical kind of pi extension. So now some final remarks about what you can do with these. So what has happened recently and what we're trying to do in the future. So Balenson also took on this project, and he has another result. So Theorem, this is also, so all our results are from this year. He didn't put it on arXiv, but I think he is finished. He's saying that, in fact, so if you take a degeneration, so a simple nodal degeneration of odd dimensional varieties, so of course curves are one dimensional, that's odd, so only it's one of the cases. Three folds would be the next case, family of three folds. Then, again, the limit mixed Hodge structure is a bi-extension. And you can define the height, again, by choosing a tangent direction or a cotangent. Then this height is related to the Bloch-Petersen height of something. So it's going to be the difference of two rulings living in the exceptional divisor if you blow up the node. That's so important of a cycle. Modulo Q log Q. So maybe if I were to write
Again, assume the central fiber is irreducible.
yeah, it's the same. So it's just I have one node in higher dimensions. Yeah, in dimension one, irreducibility I should have mentioned. Otherwise, it's just a simple node. And so in layman's terms, you could say,
Oh, sorry, this is a nodal degeneration, not a normal cross.
no, it's just it's nodal degeneration. Again, once again, the simplest possible degeneration, so that this is a bi-extension. So a formula like the one we've given here. What is the formula? Should exist in higher dimensions. In higher dimensions.
That's why he wants all dimensions so that the quadric, the exceptional divisor is quadric with two rulings.
Yes, that's why you. So in a central fiber, you have a single node, you blow it up, the preimage of the node becomes a quadric. And in the case of curves, you have a quadric in P1, and the quadric is then 2 points. And the difference of the two rulings of this quadric is P minus Q. In one dimension higher, you're in P3, you have a quadric in P3, that's a surface, and you have two rulings, 2 lines. You take the difference of these 2 lines, and you need to compute the Bloch-Petersen height of that. Difference is homologous to 0. So there are very slight conditions, never mind. Then so that you can compute the Bloch-Petersen height. And that's what he's saying, that there's a relation between these 2 heights. Of course, he doesn't give you the formula, so that's one of the things that we're working on. So maybe I point out a few future directions. One is, can we get the formula in higher dimensions? Oh, oops, I'm almost done. And so this is work in progress with same theme. And 2 is, what about more general limit mixed Hodge structures? What do they do? They also contain arithmetic information? So this is work very much in progress with Pearl's team. Okay. Anyway, I'll stop here. Thank you very much.